Hello! In case you're wondering why there hasn't been a lot of activity on my channel lately, that's because I'm working on several very time-consuming projects at the moment. Here you see me developing a new device, the purpose of which must stay a secret for some time to come. I can't tell you any details at this moment. Furthermore, I have been refurbishing the lab lately. While doing all that, I have no time to create new tutorials or any time-consuming videos. But this afternoon I decided to simply take the time and make a little video for my fans who have been waiting so long for new content. The video spins around this Rohde Schwarz frequency meter built in 1963. It is not working anymore, yet it takes away a lot of space in the lab. Since it is too heavy to be sold and shipped for any reasonable price, I will tear it down, reuse some parts and sell others. I've been planning to experiment with vacuum tubes for a long time, and for that I need a vacuum tube tester or even a whole testing environment. For that I require a special power supply for high DC voltages, different kinds of sockets and last but not least a lot of vacuum tubes. All of which I hope to find inside this unit. It is a Rohde Schwarz frequency meter named WIK-BN4421. When operational, it can be used to measure frequencies of up to 1 GHz. And can also serve as a frequency generator for up to 30 MHz. And what you can expect to find inside is the finest that 1960s German electronics engineering had to offer. The teardown begins by unscrewing some screws and pulling the unit out of its enclosure. This unit could also be mounted in a rack, like the Rohde Schwarz transmitter you saw in my videos about the isolation transformer. Inside the enclosure we find the ancestor of the modern axial fan as you know it from PCs. And we get our first glimpse on the electronics itself. As it appears, the inside of the device is entirely built from silver-plated steel sheets. Money was obviously not an issue when this device was designed. The next step in the teardown process is to unscrew various knobs and other components on the front panel. Since that is not a very thrilling process, I spare you the details. It is however noteworthy that even these knobs are very well made. They have a perfect finish and have very heavy brass inserts. Even the smallest knobs have a screw. Furthermore, we find proprietary Rohde Schwarz jacks on the panel. I will sell these, since they are rare and expensive. They have, again, partially silver-plated contacts. With some more miscellaneous parts removed and some wires cut, I can now take off the front panel, opening the view into the device. This meter has a date code from February 1963, which at this point lies 52 years in the past, and yet everything seems to be in very good condition. With the panel gone, we can also see some shielded vacuum tubes and electrolytic capacitors up here. A mains transformer and a filter capacitor down here. And here we see the two adjustment modules of the frequency meter. In the past, without any displays or LEDs, a lot of mechanical engineering was needed to build something to display the value that you were dialing in. The left unit was needed to set the frequency in megahertz, while the right one was needed to fine-tune the frequency in the kilohertz range. To measure a frequency, you would turn the axles until one of the meters on the front panel would show a positive reading. In that way, you would know that the frequency at the input jack matches the frequency you just set by adjusting the axle. Luckily, Rohde Schwarz was ahead of its time and built its devices in a modularized fashion. After unscrewing only 4 screws, I can remove the first of the modules from the enclosure. It is a closed box, which I'm sure is filled with wonderful RF magic. We will take a look inside later. Another small module that simply carries some vacuum tubes and capacitors can be removed just as easily. The heavy module on the back side is suspended on 2 metal hinges. To get it loose, I only have to remove 2 retaining rings. These days it might seem as an oddity to some people that you build hinges inside an electronic device. But a few decades back it was not a question if a device like this should be easily accessible. It was another culture of engineering, where things were built to last. This was in no way restricted to professional test gear. Even cheaper consumer products were built to be serviceable. Technical data, schematics and drawings were available. This changed in the 1980s and 90s when many German companies tried to compete with Asian competitors on the consumer electronics market. The module itself is a large silver-plated box with an army of cans, shielded vacuum tubes and electrolytic capacitors on top. We will peek inside later, just as with the other modules. Now it is also possible to remove the two parts that I called adjustment units for lack of a better term. They look like something from an old flying saucer movie. I'm quite sure that they are based on some kind of adjustable resonance circuit, but later investigations will have to show. For now, it is more interesting to me to take out the power supply unit that I hope will be a good base for my vacuum tube tester. After unscrewing it from the frame, I connected a power cord to the unit. I also removed all redundant wires and soldered some new tin on the contacts, making them more conductive for the measurements I'm going to make. Before I turn the unit on, I temporarily remove some wires from the electrolytic filter capacitors. I first measure their ESR and then their capacitance. As expected, the ESR is very low and the capacitance over the nominal value. As it appears, 52 years of age could not harm these electrolytic capacitors, even though they are usually charged to 350 volts, which is their maximum rated voltage. The reason why these capacitors have 3 legs, by the way, is that there are actually 2 caps with a common negative pin inside one can. With old equipment like this, you see that a lot. The power supply can optionally be powered from different line voltages. Since my line voltage is usually a bit higher than 220 volts, I placed a fuse in the socket for 235 volts. Otherwise, the voltage across the filter capacitors could exceed their rated value. These black components down here, by the way, are selenium bridge rectifiers, a technology that was used before high voltage, high current silicon diodes were readily available. AEG, by the way, was basically the German version of the General Electric Corporation. Now I connect the transformer to my isolation transformer unit and supply it with 23 volts rather than with 230. In this way I can safely measure the secondary voltages, at least in a ballpark way. After measuring all voltages and doing some reverse engineering, I now know the entire layout of the power supply. Via the on-off switch and a fuse, the transformer's primary winding is connected to the grid. In order to allow operation from different line voltages, the primary has 3 additional taps. By inserting a fuse in the 4 different slots we have seen before, the transformer can be powered from 235 volts, 220 volts, 125 or 115 volt lines, while the secondary voltages stay always the same. A neon lamp and the little red fan is then permanently connected to the 220 volt tap. In this way, these 2 devices are always supplied with 220 volts, no matter from which line voltage it is supplied. The primary winding is thus also acting as an auto transformer here. On the secondary side, the transformer has not 1 or 2, but 12 separate windings. The secondary windings deliver very different voltages though. The first secondary winding leads to the selenium rectifiers. In fact, it is rectified by 4 bridge rectifiers that are connected in parallel. This was done to boost their rather small rated current of 85 milliamps to a value of 340 milliamps. After the bridge rectifier, a pi filter follows. It is comprised of 2 16 microfarads electrolytic capacitors and a filter choke that is wound on a small transformer core. At both the bridge rectifier and at the end of the pi filter, voltages of around 350 volts DC are available. The second secondary winding is connected to 2 parallel selenium rectifiers, which are followed by an LCR filter circuit. Here again, voltages of around 350 volts DC are available. My guess is that the chassis ground was defined in such a way that these voltages were negative. The 3 following windings all deliver 16 volts AC. which would equate to a value of around 21 volts DC if they would be rectified with a silicon bridge rectifier and charged to a capacitor. The next 6 windings are again all delivering the same voltage. Since that voltage is 7 volts AC, it is pretty clear that these windings were used to supply a heating current to the filaments in the vacuum tubes inside the unit. If rectified, a maximum voltage of 8.4 volts DC could be expected. The last winding delivers 8 volts AC, which would equate to roughly 9.8 volts DC. These rough calculations again already consider the voltage drop across a silicon bridge rectifier. In conclusion, I can say that this power supply delivers exactly what I need to experiment with vacuum tubes. 2 independent high DC source voltages, a supply voltage for the heating filaments, as well as some intermediary voltages that I can use to power transistor-based electronics like op-amps and microcontrollers. In order to adjust the DC output voltage, a variac could also be introduced into the circuit. The last thing that I want to do today is to salvage some vacuum tubes and tube sockets from this module. First I take out the tubes. Here, this EL86 tube is held in place by a kind of retaining clip. Here, a metal shield must first be unclipped to free the tube. As you can see, the sockets have a different number of pins. The one with the 9 pins, for example, is called a no-val socket. The smaller socket next to it has only 7 pins. And we will have to talk about the many different kinds of sockets and vacuum tubes that can be found in old devices like this. After unscrewing the sockets and collecting some parts from the front panel on the workbench, I already have a nice stash of beautiful vintage components like these meters, handles, knobs and signal lamps that are all very well suited to be reused in a vacuum tube tester. Of course, the other bigger modules still hold many secrets and, better yet, many sockets and tubes. But we will have to continue our search in another video. I promise that I will take some time in the coming week and continue this project on the side as good as I can. So I hope you find this interesting and see you soon.